So this is the third video out of 4 videos for Chapter 4 for Equilibrium for Physics 12. And it's going to be the first of 2 videos where we'll take a look at equilibrium on a beam. They're both going to be looking at the same issues. The one today won't have any forces that are at strange angles. So this is the topic of the day, equilibrium on a beam. And it turns out, in addition to balancing forces like we did last day, that's not quite good enough. You actually have to also balance twists. You have to balance torques. And that's why the other day we were looking at how do you actually calculate torques. And now we can make sure that we've got them all balanced. So what we have for beams that are in equilibrium, so this is a little bit different from just points that are in equilibrium. For a beam that's in equilibrium, that could be like a diving board or a bookshelf or a bridge, a table. For a beam that's in equilibrium, we still have the first condition of equilibrium. That is exactly the same as what we had for a point that's in equilibrium. We want to make sure that all the forces add to 0. That's the first condition of equilibrium. It's best done with a little vector picture if you've got only 3 forces. If instead there are more than 3, well, then unfortunately you have to work with components. We're still going to do that, but that alone is not quite good enough. Imagine if you grabbed the bottom end of a meter stick while your friend grabbed the top end of a meter stick, and you both pulled away from each other. The forces might be balanced, but the meter stick's going to twist, right? And you might end up kind of hitting yourself in the head with it. So we actually have to do a little bit more. We need to make sure the second condition of equilibrium is actually satisfied as well. And this one says that if you check out the total amount of twist, the total amount of torque, it has to equal 0 if you want it to be in equilibrium. Now this is an interesting condition because it actually has to be met at every single point in order for it to be in equilibrium. And there are an infinite number of points on a beam. And it might sound like that's just a lot of work for you, but we're actually going to play that issue to our advantage. And we'll say, well, we probably don't need to use them all, but it's great that we've got the freedom to use any point we want. And we'll come back to that in a minute. Okay, so here's a first example of this. Let's take a look at this blue seesaw, this blue teeter-totter. It needs to be balanced. We don't want it to twist in any way. And there's a small 32 kilogram item, maybe that's a small child at one end, 3.4 meters away from the hinge. And 2.8 meters away is a larger child, but we don't know what their mass is. And we're going to see if we can figure out how big they actually are in order for this thing to be beautifully balanced and not actually move around. Now the beam itself, that blue beam, is going to have some mass as well. It's going to be 15 kilograms. And if that beam is nice and regular, then we can assume that all of that mass is in the very, very middle, right above that yellow pivot, which is going to also be advantageous for us. So that's where the pivot's going to be. That's where it actually is designed to pivot. I'm going to draw in a little triangle there, and I'm going to encourage you to do that as well whenever you're doing a beam that's in equilibrium. Okay, now let's turn this thing into a free body diagram. For 32 kilograms, if you multiply that by 9.8 newtons per kilogram, that's 313.6 newtons, and it's down. That's going to try to twist the beam counterclockwise. Okay, so don't think of it as a downward twist. Sure, it's a downward force, but think of that as being a counterclockwise twist. Okay, what else have we got? Oh, there's this other mass. We're trying to figure out how big it is, but it's actually going to be twisting the beam clockwise, even though it's also down. Now there are a couple more forces. The blue beam itself, 15 kilograms, it's going to have a weight of 147 newtons. That's going to act right where that pivot is. Now if you think about it, if it's acting right exactly at the pivot, and this is a key issue for the last half of this chapter, if a force is acting right at the pivot, at the hinge, it cannot twist it one way or the other. Because when you think about torques as being R's times F's times sines of angles, that R value, the distance from the green pivot to that purple force, is 0. So it cannot twist the beam at all. And the same is true for the normal force that pushes up. That yellow hinge will push up on that blue beam, and it's going to act right at that pivoting point. It's great to make sure it's in equilibrium up and down, but it will not twist the beam. So the only twists that are happening are from the 313 newtons. That's a counterclockwise twist. And from this mysterious weight that we don't actually know, that's going to be a clockwise twist. And so here's that second condition of equilibrium. Let's make sure that it's actually true right at that pivoting point, right where the hinge is. So we want the torques counterclockwise to equal the torques clockwise. Now for torques, you just get into this rhythm of going R, F, sine of the angle. And the angle is how that purple force meets the blue beam. Today, all the forces are going to meet at 90 degrees. So when you have a sine of 90, that's equal to 1. It's not going to cause any little interesting issues at all. And so that story would look like this. Yeah, it's a little bit long, but it's actually very, very easy to calculate. And as you work your way through those calculations, the 3.4 is an R. It's how far you are from the pivot. The 313 is a force, and then the sine of the angle. Going the other way, the 2.8 is an R. The m and the g together are the force, and then the sine of 90. Very easy equation to work with. Nothing is quadratic, and in one moment you're done, and you know that that mass needs to be 38.9 kilograms. Now we're really going to exploit that idea that when a force acts at a pivot that you're thinking about, that it cannot twist the beam because its R value would be 0, unlike the 3.4 and the 2.8s that are here. Okay, the next question. Okay, we're not going to do very many more today. Here's a table. The tabletop is 12 kilograms, and let's just say it has two supporting legs, like two broad legs, one on each side. The distance from leg to leg looks like it's 2 meters, but off center, 75 centimeters from an edge, is this 38 kilogram box that's going to be pushing down on the table. And I want to know, how much force does each table leg have to put up? I suspect that table leg number 1 has to push up with more force, but we're going to actually see what the math says. So I'm going to turn this into a free body diagram. I'm going to show where the forces are actually acting on this object. So you can't just draw a little dot anymore, you actually have to draw a beam. That way you can see where the forces will act. Well, here they all are. There are a couple of upward forces from the table legs. In fact, we're trying to figure out how big each of those are, and they're not equal. And then there are two weights. There's the weight from the 38, it's a little bit off center, and then there's the weight from the 12 kilograms. It's exactly in the middle of this 2-meter beam. Okay, I want that table to be in equilibrium. I don't want it to get up, move around, twist, or do anything strange. So I need both conditions of equilibrium to be true. So just looking back in the notes, first condition says, let's check out all the forces. Now, there are 4 forces, so I can't do a triangle, but there are no left and right forces, only ups and downs. So I just want to make sure that the ups balance out with the downs, and the ups are the F1 and F2, and the MGs are the down. So I would have this. This makes sure that the net force is 0. F1 plus F2 has to equal the mg plus the mg. There are no r's when you're working with just forces, when you're working with the first condition. So F1 plus F2 is equal to 490. That is a true equation. It's a truthful statement, but right now it's not useful because it's underdetermined. There's not enough information there to solve for F1 and find a value. I can only see that their sum is 490, so I need more information. So now I'm going to go and take a look at torques. I'm going to go and look at the second condition of equilibrium. And there's a neat little trick you can do here. So at first I want to show you maybe the wrong way to do it. So here's that free body diagram again. And no matter where I imagine there being a pivot, I'll find that the torques are actually going to add up to 0. The counterclockwise twists and the clockwise twists will be 0. So no matter where you drilled a hole in the table and made a little axle, the table will never twist. So you could start picking any point you want. This is true around every one of the infinite number of points. And you might just start picking points at random to come up with another equation. So don't copy this down. As you can see from the little title there, okay, what I'm about to do is not the best idea. So it's not worth copying, not at the moment. But I want to show you what you could do. You could say, I'll just pick a random spot, 60 centimeters in from that right-hand edge. I could. And I'm wondering, I'm worried, like, is it possible that it could pivot there, that the table could start twisting? But I don't want it to. So what's the expectation on the torques in order to make sure it doesn't twist? Well, I now have to think about clockwise and counterclockwise. Now, going clockwise would be the F1, and only the F1. That would try to twist the beam clockwise around that green pivot. This 372 will actually try to twist it counterclockwise. So will the 117. But even F2, which is up, will also create a counterclockwise twist. If you imagine lying your pencil down on top of this little picture and applying those forces, those 3 forces will all twist it counterclockwise, and only F1 is clockwise. So again, this is still not the best idea, but this would work. You could say, I want to make sure that the counterclockwise CCW, counterclockwise torques, are balanced out by the clockwise torques, that CW value for the torque. Okay, here goes. I've got 3 counterclockwise and 1 clockwise. And each time I'm going to write down an R and an F. So if you start running through the numbers, right, you'd have to be careful about this. But if you were, you go back to the original picture and say, oh, okay, the whole beam is 2 meters long. And that 372, okay, looking back at the original picture, 75 centimeters in from the edge. And if you start doing some subtracting, you'll see it's 65 centimeters from that little green pivot that I arbitrarily picked. Totally arbitrarily picked it. So you would go R times the F of 372. Now I didn't have enough room, but I probably should have put in times the sine of 90. But if it's the sine of 90, it's not going to change anything. The next one, if you carefully do your subtracting, you'll see that the middle of that tabletop is 40 centimeters from that green triangle, that little proposed pivot. So I go with an R and an F and a sine of 90, which I was too lazy to draw in. And one more. It's 60 centimeters from that green triangle, that totally arbitrarily chosen pivot, out to that F2. So 0.6 meters away is the R, F is the force, sine of 90. And then going the other direction, it's 1.4 meters to F1, and then the value of F1. This is a true equation. It has 2 unknowns in it, and it can be tidied up until it looks like this. Now, I still don't think this is worth copying down because it's too messy, but it is truthful. So now you have this second equation that you could actually use in your problem solving. And so you've got your first equation already, just from balancing forces. And now we have this second one as well. And so by putting the 2 together, you could do it. It's a whole math 10 game. 2 equations, 2 unknowns. You could go and have some fun with that and it would work. But it's not very much fun trying to do some substitution or linear combination to make that work. Here's a better way. And it comes back to the fact that on that seesaw, the forces that act at the hinge cannot do anything at all. So here's the way you do want to copy down. This is the best way to go. What if we pivot at one place where there is an unknown force? Now the 2 unknown forces are at the table legs in this question. Sometimes they are at the edges of the object, like today on this one, but not every time. Okay, so look around for an unknown object or an unknown force and put your pivot there. So I'm going to propose that we just pivot at leg number 1. And basically what I'm saying is, on this free body diagram you've got there, just draw in a little triangle there and say, hey, I'm worried. I'm worried that it might start twisting there. And now, because you put that pivot there, this F1, and you don't know how big it is, it cannot create any twist for that pivot. So you don't even have to talk about it. You can just talk about what F2 would do. That would create a counterclockwise twist. And then the 2 MGs, they would create clockwise twists. The only thing now to establish is how far is it from that pivot that you've declared out to each one of those forces. So you have to grab your tape measure and start measuring that. But that's not very hard to do based on the picture. So pivoting at leg number 1, you could also have pivoted at leg number 2. But pivoting at leg number 1, when I balance my twists, here's what I find. The equation looks really long, but it's very easy. Walking through it, this 2, it's 2 meters from that pivot out to F2. So there's the R, and then here's the F, and then the sine of 90. Now, twists going clockwise. It's 0.75 meters from that table leg where you drew the pivot out to where the 38 creates a force. So 38 times 9.8 is a force, and then sine of 90. The 1, this one's important. I'm going to go back to the picture. It's 1 meter from where we put this arbitrary pivot to the middle of the table. It's a 2 meter wide table, looking at the numbers up here, and it's going to be 1 meter to the middle where you can pretend all of the 12 kilograms is located. That's how center of mass works. So that's where the 1 comes from. 1 meter to the middle of the table, 12 times 9.8 is the force, and then sine of 90. Yes, it's long, but it's linear. There's no quadratic, nothing is squared. It's actually very easy to solve. You solve for F2 and you find out it's 198 newtons big. Now, there are 2 ways you could figure out how big F1 is. You could say, hey, that was so much fun. I'm going to start over again, this time pivoting at the other table leg. Absolutely works. The faster way, go back to this equation that's just been sitting here stewing, just kind of waiting for you to do something with it. And now you can go and substitute in the 198 in for F2. And then you can find out how big F1 is. And you're done. So that torque method is very, very valuable, especially if you pivot at an unknown force. Okay, let's do one more. This one is from your textbook. Okay, took the picture from there. Got this girl on the diving board, and I think the intent of the picture in the book was for her to be located right at the end of this. Well, it's a 4-meter long board overall, and it's got those supports way back over on the left-hand side. She's going to have a mass of 65, and the board itself is going to have a mass of 35. And you can pretend all of that 35 kilograms is located right in the middle of the board, 2 meters in from either side. Okay, need a free body diagram showing where all the forces are. Clearly her feet are going to push down, and the weight of the board will be down. What happens at the supports is a little bit interesting the first time you see it. It turns out one force is actually up and the other one is down. The force at the very left side of the board is actually a downward force on this cantilever, right, stopping the board from flipping and dropping the swimmer into the pool. Now I'm going to show you in the end that if you'd accidentally put both of those forces up, you'd still get the right answer if you were careful, but this is the ideal way to do it. So we're going to go into our conditions of equilibrium. First one says forces up equal forces down, so there's a force up, and here are some forces down. Let's go and see what that does. Okay, that gets us to here. It's not solvable for a value. You can't say, oh, wow, look, F1 is this many newtons. But at least you have this relationship. And that can just sit there and stew for a little bit, and we'll come back to it after we've done some work with torques. So for torques, we need to pick a spot to put the pivot. Two good places would be at the location of F1 or at the location of F2. They're both acceptable. But once you pick your location, when you measure your R's, you have to measure from that location, wherever it might be. Either is fine. I'm going to pivot from here. So now for my F1, I don't even have to worry about it. It can't create a twist. F2 is 1 meter away. The mg for the board, it's in the middle of the board, and it was a 4-meter long board, so it's 2 meters from the green pivot. And then her feet are going to push down 4 meters away. F2 will create a counterclockwise twist around that green pivot, and the 2 mg's are going to be clockwise for this picture. And so I set up that story. I'm going to demand that the counterclockwise twists equal the clockwise twists. And I have this. Again, it's a little cadence, a little rhythm, the R, then the F, and then the sine, but it's the sine of 90 today for all of the examples today. So you don't even have to put it in. The R, and then the F, and then sine of 90. The R, and then the F, and then the sine of 90. Very quickly you find out that F2 is very large, 3,234 newtons. And now we can go back and deposit that in here, do a little substitution, and we can figure out how big F1 is. And so we have those two values. We already knew that F1 was going to be down and F2 was going to be up, and now we know how big they are. Now, final thing, you don't have to copy this down. I just wanted to show you this. What if you didn't know that that first force was a downward force? So I'm just going to show you this. You don't need to write it down. But what if you'd accidentally drawn it like this? What if you thought that F1 was up? It turns out if you're careful, the math will tell you that you've got it wrong and fix it in the end. At the beginning, when you balance ups and downs, you would have thought that both of these were up. And so you would have had this, and that would just sit there. You would go through the same process we did where you put the pivot in and find that value for F2. But now when you go and substitute back into this equation, it's a little different looking than the one we actually wrote down in our notes. And you would find this negative would show up. And it would basically be saying to you, hey, whoa, be careful. The way that you had drawn it was wrong. Here's the right answer, 2,250 newtons, but it was the opposite direction to what you thought. So you'd still get it right, even in the end. Okay, but it is best if you can draw that picture going the right way. Next day, we're going to just highlight a few stories where the angle might not be 90 degrees, but it's basically going to be the same plan. Just working with the first and that second condition of equilibrium.